relevant to the life cycle of a star. Whether for millions or billions of years, stars can and will outlive every human who has ever lived and will ever live, as our lifetimes are merely like the snap of someone's fingers in comparison to the life of a star. But what is the life cycle of a star, and what is stellar evolution? Let's start at the beginning, the way beginning, just for some context. Astronomers and scientists today believe that the universe began with the Big Bang, where the entire universe was compressed into an infinitely small point, which was also infinitely hot, dense, and with an infinite concentration of energy. After the Big Bang came the Planck era, where everything was so small and dense that our modern physics fails us. The universe would go through a few more eras, those being the gut era and electroweak era, before the universe would cool enough for particles and matter to exist. This leads us to the particle era, where particles begin to exist. After this and a few more eras of the universe, those being the era of nuclei and the era of atoms, we finally come to the era of galaxies, where stars and galaxies start to form and our story truly begins. The life cycle of a star begins with an interstellar gas cloud. The gravity of these clouds eventually would collapse in on themselves, and these gas clouds would get smaller and denser and hotter until hydrogen fusion would begin and a star would be born. As said by Priya Hassan in her article Starlight and Darkness, the Russell-Vogt theorem states that mass and chemical composition are the two important parameters that decide a star's fate. If we take our solar system star as an example, the Sun, we can see one way a star can live its life on the main sequence. A star's life on the main sequence is determined by how long a star fuses hydrogen into helium. The Sun will stay on the main sequence for about 9 billion years before running out of hydrogen to fuse, then turning into a red giant, before finally becoming a white dwarf. As I said before, when hydrogen in the core of a star runs out, and hydrogen fusion finally finishes, the core of a star will start to collapse. With the collapse of the inner core, these stars will veer off of the main sequence and become red giants, and the core will still continue to become denser and hotter until it eventually becomes a white dwarf, when the core runs out of helium. This is what's known as the horizontal branch star. These stars then cool off over billions of years into black dwarfs. An effective tool to study stellar evolution is the Hertzsprung-Russell diagram, which was created by two scientists back in the early 1900s, called Agnar Hertzsprung and Henry Norris Russell. The Sun is our classic low-mass star, which we have already given as an example. But how do high-mass stars live their lives through stellar evolution? High-mass stars, like their low-mass counterparts, also fuse hydrogen into helium, but do so at an increased rate with the help of other elements like oxygen, hydrogen, and nitrogen. These high-mass stars will eventually become supergiants, but the high temperature of the core means that helium will fuse with iron and other heavy elements, and this will lead to the end of fusion for the star, as fusion cannot occur with these heavy elements. The end of the fusion is the end of a star being on the main sequence, and a supernova explosion will occur from the collapse of the core of the star, of this high-mass star. And what we've learned from this is that the mass determines a star's lifetime, along with its ability to do fusion. And at the end of the day, when high-mass stars die and turn into supernovas, a black hole is formed. Many astronomers today subscribe to the belief that the universe will expand forever, and one day, when all the stars die, we will be left only with their remnants, black holes. But that's a story for another day.